right, so welcome to the first seminar of this year. So we have the pleasure to host Tobias Nipkow. So Tobias is a professor at the Technical University of Munich, and he's famous for his work on mechanized proof, especially as one of the authors of the Isabelle HOL logical framework and proof assistant. And he's been using Isabelle HOL to specify and verify. You got many theories ranging from pure mathematics to algorithms and programming languages and tools. In particular, well, he's kind of the founder and head of the Archive of Formal Proofs, which is a very nice, very well curated collection of mechanized proofs in Isabelle HOL. And coming closer to the topic of this year's seminar and course, some of his recent work involves the verification of functional data structures, both for functional correctness and complexity. And so he's the main author of this functional algorithms verified textbook that is recommended reading for my course anyway. So, well, thanks a lot, Tobias, for coming today. And the floor is yours.
So good morning, everybody, and it's a great honor and also a great pleasure to speak here. Thank you for inviting me, Xavier, and this is the first time I have the opportunity to be at Collège de France, and I hope I'll be able to tell you something interesting. Xavier already, yes, there it is. Yeah, so this is just another snapshot of the cover of the book, and it's with a lot of co-authors, and it's a compendium on functional data structures and algorithms, formally verified, and correctness and complexity, sometimes also the amortized running time. And it's definitely inspired by existing books, in particular the one that is very important for this course as well, Okazaki's textbook, or not more than textbook, Okazaki's monograph on purely functional data structures, but also from the big brother of algorithms, which contains a lot more material, but from an imperative world. And the book contains textual proofs, but online you can also find the machine-checked proofs. And the topics, here's the quick list, and it's growing, so I'm on a sabbatical at the moment and hope to add further topics to the book before it'll eventually be published, well, probably sometime next year. And what I want to talk to you about first today is just the quite simplistic modeling of running time in our verification efforts. Then two examples that I will go through in detail, real-time queues and real-time double-ended queues, and that follows on directly from what Xavier has been talking about this morning. And finally, if there is some time, but probably there won't be, then I'll talk about skew heaps, which Xavier would have talked about if he had time, but he didn't. So first the time aspect, and the idea is simply that I equate running time complexity with number of function calls, and that's a standard measure in the functional programming community, and you can argue whether this is a good measure or not. I'm just going to go by the traditional way of doing things. And that means for each function from tau to tau prime, there is another function, tf, that takes the same type of arguments but produces a natural number, namely the number of function calls that had to be executed while computing f of that argument. And the idea is that in the end, it doesn't really matter whether you argue about f or tf. You use the same kinds of mathematical principles, inductions, case analyses, equation logic, etc. So as long as you have those two functions, you don't need to know that you're reasoning about time. You're just reasoning about some mathematically defined function. Of course, the key question is, where does that time function come from? And the example to demonstrate how to make the transition from the function to the time function is this this piece of code. So I am not using any particular programming language. I'm using a kind of a mixture of different notations. And I think the one thing that I do need to point out is that the hash sign is the cons operator in my notation. But everything else I think is pretty similar to OCaml. And if you have that function, which happens to be the append function, then what does the time function look like? Well, the structure is very similar, except that in the base case, you don't return the actual value, but you return the number of calls that you needed to compute that value, and that was just one call, the function call itself. And then in the cons case, you have the time for the recursive call, tf of x's and y's, plus 1, where one of the two ones comes from the fact that you had to execute a cons operation, which we assume to be constant time. And so constructors are assumed to be constant time functions, and then another one for the function call itself. You can think of this as an abstract interpretation, T of f being an abstract interpretation of f, or you can compile one to the other, and that can be automated. And you can also simplify matters, and that is not unimportant if you want to have an easier time verifying things. Oh yes, this automation for a call by value language is quite easy. For a call by a lazy evaluation, it's much more complicated to automate the translation or the derivation of the timing function. But throughout the talk, I will be focusing on call by value. And in order to make things easier for the verification, you can also reduce all the additive constants down to 1. So instead of the 1 plus 1, you just have 1. That's, of course, something you have to justify at a meta level, that that's OK and doesn't change the O of running time. An alternative, less, say, error-prone approach, because here you do have this intermediate step between the function and the timing function, and you may have made a mistake in deriving the one from the other. A monadic approach can avoid that. So we define the two functions simultaneously, but we do it in a monadic framework in order to hide the time component. And so we define the function in reality on value time pairs, but when you look at the notation, it'll be monadic and you won't see the time explicitly. And you use the basic combinators. The return would return the value and a 1. So here is where you charge one time unit for the function call. You charge it at the end to make it slightly simpler. Actually, in reality, we do it a bit differently, but that's one way of doing it. And then the bind for the monad, you start with a monadic value of a value a and a time m, and you apply f to that value, which means you apply f only to the a component, and then you return the b result and the sum of the two times, the time that you already got from the input and the time that it took to compute f of a. That can be sugared with the usual do notation that we know from Haskell, and then it looks more like an imperative program where you compute sub-expressions one after the other. And here is an example. You define your algorithm monadically, so here, and then you derive the two functions, the value function and the time function, by just projecting on the respective results. And here's an example. So this is what our append function would look like, a monadic notation. You return the empty list in the base case, and otherwise you first append the two sublists, and then you return x cons the result. And then you can get the original definitions relatively easily. And in fact, if you really want, and you do want, you don't want to work with this version or this version. What you want is the original recursive versions to work with, because those are the ones that you will have to prove things about, and you don't want to prove, have the time have the time component get in the way when you just want to prove something about the value. And so what you do is you can derive the original definitions quite easily. In fact, that can be automated. And that's actually all I wanted to say about the time. And mostly, unless we get to skew heaps, I will just be talking about persistence and constant time access. No, I don't know. Forget the access, I don't know what's there. So persistent and constant time execution, I think I wanted to say. And therefore, there is no need to analyze time. Why? Because all the functions I'm going to show you will be non-recursive, so they are obviously constant time. Doing an explicit analysis would be a bit of an overkill. But of course, you could do it. And so the two examples I will show you, the real-time queue and the real-time double-ended queue, they are in that realm that all the operations are constant time and they are non-recursive. And so now I follow on directly from Xavier's lecture, real-time queue, and just to keep my slides self-contained, there'll be a few slides that you have seen. So this is a queue where you enqueue on one end and you dequeue on the other hand. And then, of course, in a functional language, the question is how do we implement that efficiently? And of course, a list comes to mind, but then the problem is either the enqueue or the dequeue operations will take linear time because you have to get to the end of the list. And so the answer is how to do it more efficiently. Use two stacks, one for enqueuing and one for dequeuing. But so this is what we call the rear, where you enqueue, and the front, where you dequeue. But of course, what happens when the front becomes empty? Well, you need to reverse the rear, and that takes linear time, which is okay if you're interested in amortized complexity, because then you look at the complexity over a whole sequence of operations, and then this one expensive operation is compensated for by many cheap operations, and in overall you get constant time. So that's fine, but of course the challenge is how to do a real-time queue, real-time meaning where all the operations have worst case constant time, running time. And real-time, of course, because if you wanted to use these queues in an operating system, in a real-time operating system, you would want those real-time response guarantees. And one solution, the one that you are now familiar with, is laziness. But it's in red because we don't want that for this lecture. And so how should we do it? If you have an eager language or a call by value language, if you have OCaml. This is how it was proposed by Hood and Melville. The solution is in principle quite simple. You don't wait until the front becomes empty, because then it's too late. You have to reverse the rear, and that will have linear time complexity. But you compute this new front, which is the old front appended with the reverse of the rear, early and incrementally. And of course, at that point, when you do that early, the front isn't empty yet. So you're doing it when both the front and the rear are non-empty. And this is what you want to compute, but you do it incrementally, meaning you don't incur the overhead for reversing all at once, but you incur that slowly over time. And that's the whole trickiness of the business. And why can you do it incrementally? Well, here is the concrete example, incremental reversal by a pair of stacks. You just keep on taking one element from the one stack and pushing it onto the other stack. and then lo and behold, after 3 steps, you have the reversed one of the 2 stacks. By the way, I will mostly, when I say stack and list, that will be more or less interchangeably, except in one place where it really does make a difference, but otherwise I mean the same thing. You do that in parallel with all the other InQ and DQ operations. There we are. And so what you have essentially 2 copies, except that they aren't copies. You have 2 versions of the front and the rear, and because of persistence, you can have them both, and you can manipulate them, and one won't interfere with the other. But this process here of computing this expression incrementally using the shadow is done on the shadow queue, and then there is another queue, which is where the actual InQ and DQ operations happen. And with every InQ and DQ, you perform the InQ and DQ on this new queue, but you also perform one of these steps here. And hope that you get to finishing the computation of that before the new stack again requires you to the new queue again requires you to is faced with an empty front. So this is the reversal strategy. This is what we want to do. R and F stand for rear and front. And we want to, in the shadow queue, start with the current rear and front, and after a finite number of steps, end up with the computation of front, append, reverse of rear. And this happens in 2 phases, actually quite simple. You first reverse the rear. In the number, it takes the number of steps that the rear is long, and R prime is the reverse of the rear. And in parallel, meaning, of course, you don't need a parallel language, you just do these 2 steps one after the other, but in one InQ or DQ step. And you also reverse the front. And so F prime is the reversal of the front. Why do you reverse the front? You don't need to reverse the front. Well, you do, because now you reverse the front onto the rear. So you have, in the first step, you've computed those 2, and then in n steps, you are reversing F prime, so onto R prime. So you get ref of F prime, append R prime, but then you remember what F prime and R prime are, and then in the end, that's the same as saying it's the front appended with the reverse of the rear. So this is the basic idea of how to distribute this overall computation of front append reverse of rear over, well, how many steps actually? Here we need the maximum of the 2 lengths of the 2, and here we need again the length of the front. So it's basically front M and maximum of M and N added together. And when do we start? Well, I'm not going to just go into the exact details why, but the right answer is when the rear is 1 longer than the front. So which actually is, if you start with an empty queue, then if you InQ the first element, then you already have that situation, which is clear, because now when the next DQ comes, you need to have moved that over. That's one motivation. And then in the end, the length of everything works out. And so that means you require n+1 steps for this first phase and n steps for the second phase. So you need, we need to finish before the original front becomes empty. The original front had n elements in it. Now we need 2 n+1 steps, so that means that roughly we need to perform 2 steps per InQ or DQ in order to get from this situation to this situation in time before the original front becomes empty. And of course, there's one initial step because we have 2 n+1. That's the whole idea. And there are some complications. how do we dequeue from, sorry, this is not the complication, this is how we do it. So we have both these two, in quotes, copies, shadow queue and original queue, and how do we dequeue? Well, the dequeue operation simply dequeues from the original front. No problem about that. But the problem is that you would also need to take that element out of the shadow queue, because in the end it shouldn't be there anymore. But that's very difficult, because in the shadow queue it'll be somewhere in the middle. So the nice thing is you just need to remember how many elements have been dequeued in the time when you started the reversal and ended the reversal, or rather, in fact, you can end the reversal early because you know, oh, some of these elements are no longer valid. They have already been dequeued. So in fact, you need to remember how many elements are still valid. And if that has gone down to 0, essentially, then you're finished with your shadow queue reversal. Another complication is that what do you do about in-queue? Well, you start a new rear and you in-queue into that. But then you have to ensure that your reversal is fast enough so that that you have to ensure that the new rear is in size less or equal the new front, because that's an invariant that you want to keep. So you have to make sure that the number of in-queues you can do here into this rear doesn't break this invariant. But it does work out, so all the arithmetic works out to a T. But that's the kind of thing that mechanized theorem proving is good at, and paper is less good at. And now I'm going to show you the implementation, but I will just click through it to give you an idea of the complexity of the implementation. You can also compare it mentally with the complexity of the much simpler implementation with laziness. And so you have a shadow queue, which has these two phases, reverse and append. And then this is a step in the shadow queue. And here you invalidate an element in the shadow queue. And here's the whole queue, which contains the shadow queue here and the new front and the new rear, and also length counters, that so you don't never have to compute the length of the queue, because that would again be a non-constant. And the in-queue and dequeue operations are very simple, except that there is a check operation. Oh, there are these. Yeah, there's a check operation, which is more complicated. And in the end, it's not completely trivial. If you thought about it long enough, then you're quite sure that it works. But it would be nice to have a really bulletproof proof. Before I show you, well, I won't show you the proof anyway, but I'll show you what I'm going to prove. And here's a short explanation of the specification style that I'm using, because when Xavier introduced stacks, he also talked about algebraic specifications and how stacks have satisfy certain algebraic laws. This is, in the end, it looks similar what I'm doing, but it follows a different philosophy. And the philosophy is you have a model-oriented specification. That means you don't pull algebraic laws out of your hat, but you say, oh, I have already an abstract mathematical structure that fits exactly what I want to do. And then in our case, we say, okay, yeah, the structure that I want to model in a queue is just a list. Remember, here we're talking about the functional correctness that we're verifying, so not the complexity doesn't need a specification. So you say, okay, queues are just lists, and then you assume you have an abstraction function from queues to lists. Let's call that alpha. And then you specify, this is the specification that you're given. For each operation on the queue, you give a corresponding operation on the list, or you realize your queue operation by a list operation. And so there's one correspondence there. And formally, in fact, what you're saying, I'm not showing you the text here, is that yes, that the alpha, the abstraction function, should be a homomorphism from the queues to the lists. And then the correctness proof of an implementation, well, you have to define your abstraction function for your very specific implementation of your queue, and then prove all the correspondence properties, that this operation on queues is realized by that operation on lists, and that that is actually correctly realized. And here is a simple example. So this is the queue specification that I'm building on. So we have these 4 operations. I tend to talk only about enqueue and dequeue because they are the interesting ones. Then we have an abstraction function which we call list that goes from queues to lists. And we have also an invariant because typically not every representing data type is a valid value. And so you single out those values in the implementation that represent valid queues. And then the specification just consists of a list that's as long as there are operations, namely the correspondence requirements that enqueue implements append with a singleton. And so that means if you abstract with the list function the result of enqueuing, that's the same as abstracting the argument and then appending the element to it. And you do that for all the operations. So the dequeue operation corresponds to the tail operation. The first operation corresponds to the head operation, and so on. And that's essentially the specification. That's what you have to prove. So the correctness proof is actually quite easy because all the functions are non-recursive. What could be simpler? Well, this isn't quite true because the specification will also involve functions, not just the specification, the specification including the invariants will also involve recursive functions like append, reverse, take, drop, and then you need all of those properties, how they relate. So there's some bit of recursiveness in there, but the program itself is non-recursive, which gives us the constant running time. But in the end, it is a tricky proof because of the invariant, which you first have to find, and the abstraction function. But it's not too bad in the end at 700 lines. And I think most of the time Alejandro spent on figuring out the invariant. And so this is, now I'm just flipping through the invariant. And so you can see you have to figure out these things here. And it's not immediately obvious. Yep. And the inventors of all this whole gadget were Robert Hood and Robert Melville in '81. They published this, and Robert Hood was a PhD student at, not Carnegie Mellon, the other one, New York State. Anyway, yeah, some US university. And I don't know how Robert Melville actually got involved, but the main author is Robert Hood. And I think the verification, which is actually part of the book, may not be the first one. Maybe other people have verified the Hood-Melville queue as well. I'm not sure about that. Now let's go one step further and look at real-time double-ended queue. So what is a double-ended queue? Well, it's like a queue except that you have now 2 different enqueue and dequeue operations. You can enqueue on the left, or you can enqueue on the right, and dequeue on the left and dequeue on the right. So you can imagine that complicates matters somewhat. And the implementation, of course, again will be 2 stacks because you want constant time enqueue and dequeue. And most of the time this works in constant time, of course, except one of the 2 of them gets empty. So in fact, you have amortized constant time even if you get them empty. And if your stack becomes empty, so here, for example, what do you do? Well, you could follow the example of the previous one and reverse this stack, except that then you could easily get into a back and forth reversal because you can enqueue and dequeue on both ends. So what you do is you reverse the bottom half. You reverse only half of the stack, and so then you're immune if you were to put all of this here, then of course the next time the opponent would dequeue there and you'd have to put it back. But if you split it in half, then you can't lose. You get amortized constant time. Well, there is actually in the book by Okazaki, there is a version with laziness, but then the question is, how can we implement it if you just have eager evaluation, no references? And this is the solution. Again, we don't wait until the double-ended queue has become empty, but we start reversing when it becomes too unbalanced. What does that mean? Well, we have to look at, and then if it becomes too unbalanced, then we move the part of the bigger step to the smaller stack. Yeah, that makes sense. But what does too unbalanced mean? Well, we should aim at the end of the reversal process that the two stacks have the same size, or roughly the same size. And so this is a concrete example. If you have 9 elements here, and then your this stack here has only 3 elements, then maybe it's time to reverse. And what you would do is you will reverse 3 elements of this stack onto this one, and then you would be left with 6 and 6 on both sides. And so that gives you a very concrete idea of what it should look like. And this is the general situation. If S is the smaller stack B the bigger, and M size of smaller, and the size of the bigger, then the main invariant is that 3 times the smaller stack should be greater or equal than the bigger stack. And when can it happen that this invariant is destroyed by an in-queue or a d-queue operation? Well, roughly speaking, when we are right at the border, when 3m is almost equal, well, it's supposed to be a little bit bigger than greater or equal n, but if they're equal, for example, then the next d-queue operation on the smaller side would destroy it. We're not going to go into the fine details of +1 or +2, so we just work, that's what this symbol indicates. And now here's the rebalancing strategy. If B is the bigger stack, then we separate, just conceptually, the bigger step into 2/3 at the front. That's why it's called B12, and the last third at the back. So this has got size 2m, and this has got size m, where m remembers the size of the smaller stack. And so all we need to do is move B3 behind the smaller stack in enough operations to do it quickly enough in order to avoid what situation? The smaller stack has size m, and so after m dequeues, you have to finish that reversal. So this is the aim. The big stack loses the end, and the end is reversed onto the smaller. For space reasons, I'm now using the back arrow to indicate reversal. And this is the start situation. What do we do first? We do a reversal of the beginning of the big stack. That takes 2m elements. 2m steps, because that's the size of the first 2/3 of the big stack. And in parallel, we also reverse the small stack. So here we have separated the one big stack into the reversal of its front and the remaining back. And we have reversed the small stack. And then we reverse this once again to get back the B2 that we want, B12 that we want in the end. But the B3 is something we can work with. And now we can combine those two. How do we do that? First, we reverse B3 again. So we get B3 reverse. And then we can combine those two in the way that we've seen before by doing what? Well, this is where we want to get. So we have to reverse this one onto this one. And that's another m steps, because we assume the smaller one has size m. And if you now add up all the steps, so you have 2m steps in the beginning, and then you have another 2m steps, because this, of course, happens in parallel, and these are again 2m. So you have 4m micro steps that you need. And that means for each in-queue and d-queue, you have to perform 4 steps, and 4 steps of whatever phase you're currently in. So you see, we also have 2 phases, but it's more fine-grained now, and that's what makes this verification also more complicated because you have to distinguish many more situations. And so again, we have two decks, the shadow deck, where the rebalancing happens, and the InQ and DQ deck, where the current deck operations happen that happen in parallel with the reversal. And then there are a number of complications. What do you want at the end of rebalancing? We need to combine the result of rebalancing and newly InQ'd and DQ'd elements. Because you have InQ'd elements and not DQ'd, just InQ'd. You InQ and some elements, and then you reverse, but that means you now have two lists. You have a list of newly InQ'd elements, and you have this list that's the result of the reversal. How do you combine them? Well, without, of course, using append. And so what you now do is, this is where stacks actually are no longer lists. Some of the stacks that I haven't told you the details. Some of the stacks that you see are actually pairs of lists in order to avoid appending those. And then you have to make sure that that if you again combine one of those stacks with the simple stacks that are lists, that you've got to the point where one of the two lists has become empty. So it is really a lot of bookkeeping that you have to that you're involved with. But when I started reading this, I thought, okay, maybe you need triples and quadruples of stacks. That sometimes no, pairs is enough. Why is this not a problem with the real-time queue? We didn't see any complication like that because the real-time single-ended queue, one of the two stacks, the rear becomes empty, and so there's no problem with appending. But here, at the end of the reversal, both are non-empty, and so that's why adding the newly InQ'd elements to them is another complication. Another detail, DQs of size less than or equal to 3 decks, not DQs. Deck is a nice name, but if you have DQ and decks in the same sentence, it becomes a bit confusing. So the double-ended queues of size less than or equal to 3, they are just represented as normal lists. So those are boundary cases. No problems. Let's just do a quick check that it seems to work. This is not a proof, but at least we sort of tick off the main complications that could arise. Rebalancing needs m steps because after m steps, one of the two, m is the number of the size of the smaller stack. So after m steps, that stack could have become empty. And so it yields two stacks of size 2m each. That's the rebalancing. Now, two extremes could happen during rebalancing. You could have m times an InQ operation at one of the two ends. Why is that something to watch out for? Because then, in the end, the stacks have size 2m and 3m. 2m is what the reversal, the rebalancing gives you, and another m becomes because you have done lots of InQs. Why is that okay? Well, we have to check that at least at the end of this rebalancing process, our invariant is again satisfied. The 3 times smaller, greater, equal, bigger. And that is the case. 3 times 2m is certainly greater equals 3m. Another extreme could be that you have only DQ operations of the smaller stack. And so what happens then is that the smaller stack has m elements, so that's okay. We don't get to the bottom of the smaller stack before the rebalancing ends. That works. Is the invariant satisfied? Yes. Well, the two stacks have size m. Well, they had 2m, but you have to take the DQ into account, so only one of them has just size m, the other has size 2m. Again, the invariant is satisfied. And so that is a sort of a back-of-the-envelope calculation that at least the main invariants seem to be satisfied. The full story is a bit longer, so the code is about 500 lines. That's with spaces and a few comments and things like module headers. But it is sizable, and the correctness proof is also sizable and involving all the invariance, abstraction functions, and so on is about 4,000 lines of proof. So this is definitely not something not a piece of code I would trust without a very detailed proof. This is based on the code by Zhang and Goldberg that was published at FPCA 93. Some of us still remember before the Functional Programming, International Conference of Functional Programming was called Functional Programming in Computer Architecture, but I think there was always very little computer architecture there, and that's why they dropped that. And that's the code, but their proof is basically at most at the level that I've given you, the correctness proof. And then it turns out that they, without realizing it, they had reinvented something. Namely, if you look into Robert Hood's PhD thesis, there is also the top-level sketch why this would also work for double-ended queues. But apparently, they're in good company. Other people have also reinvented this. And so Robert Hood seems to have been the first one who did it for the double-ended queues. But then people, unknowingly reinvented. Yes, now the question is no, I don't think. Should I go into skew heaps? I could do it quickly. Yeah, okay. Then let me quickly change gears and give you a very brief introduction and a view of the correctness proof of the skew heaps. And that's, as Xavier already introduced, it's a self-adjusting heap, a priority queue, but actually implemented as a heap, meaning it's a binary tree, and the smallest value in each subtree is always at the root, which means you can very efficiently extract the smallest value. The insert function, there's a merge function, which will be crucial, and the lead min function to get the minimal element. They have amortized logarithmic complexity, logarithmic in the number of elements of the priority queue. Insert and del min can be defined from merge. So that's the key, that shows that merge is the key operation, and the other two can easily be implemented on top of it. Why is del min implemented on top of merge? Well, imagine you have a heap and you want to take out the minimal element, then of course what you do with the two subtrees, you have to merge them. That's how the skew heap works. But the trick of the skew heap is that it does the merging in a way that gives you amortized complexity. So yes, implementation type is just ordinary binary trees. The invariant is it's a heap. And the merge function, well, these two clauses are obvious. This is my notation for the empty tree. And then comes the more interesting question, what if you want to merge two non-empty trees? I guess I should do something about this being called H. I couldn't make up my mind whether it should be a tree or should be a heap. And it shows up on those two lines. So what do you do when you now want to merge two non-empty heaps? And the very simple idea is that you swap the subtrees when descending. And so this is the complete code. And this is, again, my own homebrew notation for giving this pattern here a name. So merge is a merge of T1 and T2, and both T1 and T2 are supposed to be nodes with an element in the middle and a left subtree and a right subtree. And what you do is, well, first, of course, the smaller element has to come to the top. This is just a comparison. Let's assume A1 is the smaller element. So you get, in the end, a tree that has A1 at the top. And then you merge T2 and R1. So here you have performed a swap. R1 used to be in the first argument. Now R1 is in the second argument. T2 was the second argument. Now T2 is the first argument. Similarly, L1 used to be the first argument, is now in the second, in the right tree. And magically enough, that gives you amortized complexity. And I have to, I'm afraid I have to disappoint you. I can't give you a good intuitive argument. It's one of those things where I would say, well, you just have to do the math. And we did the math, and the correctness proof is not interesting. That's straightforward. But the logarithmic complexity, that is interesting, and this is the key theorem, that the time for merging plus the difference in potential. This is slightly interesting because it's a function that takes two arguments. And so the difference of potential, what is it? Well, it's the potential after the merge minus the potential of both arguments before the merge. Not too surprising, but sort of not completely standard, is bounded by the logarithm in the size. This notation is the number of leaves of both subtrees. And the complication is that you have to invent lots of nice functions. So right-heavy counts. The right-heavy is a function that gives you 1 or 0, depending on whether the tree is right-heavy, meaning the right part of the tree is bigger than the left part. And then we also have this is the number of right-heavy nodes on the left spine. So the L stands, you go down the left spine, and you count the number of right-heavy nodes. And then you get some nice lemma about the complexity, the number of those counts and the size of the tree. And you get easy corollaries. And then you can do it just the other way around, going down the right spine and counting the left heavy. And you get the same corollaries. And then you can define the potential. And the potential is for a non-empty tree, it's the potential of the two subtrees plus the number of right-heavy nodes on the left spine. And this is not something I came up with. This is actually something we did find in the literature. I'll say a bit more about that later on. So at least I can give you this much intuition. Merge descends on the right. Maybe you didn't notice, but that's what it does. It descends on the right spine of the two trees, and therefore the right heavy nodes are bad because then it has to descend longer, and therefore they count into this potential here. And the key auxiliary lemma is this one, which I don't think I would ever have come up with, where this is the potential at the time plus the difference in potential, but this is a completely new expression which uses all these auxiliary functions. And that goes through fairly, well, that goes through automatically. If you want to see the full proof, here it is. No, you didn't want to see the full proof. And the main proof does not go through automatically. It's some reasonably simple manipulations of logarithms, and at some point you need some laws about logarithms, but in the end it comes out fairly quickly. So this is something you can still present in a lecture. The double-ended queues in a call-by-value language, I would not want to present all the details in a lecture. This, of course, was invented by Sleeter and Tarjan. It's at the very beginning of this amortized complexity invention and of amortized complexity. And then the formalization, because if you read this paper, I would have found it very hard to extract the nice algebraic formalization, but two people did it before me, and they came up with the algebraic formulation, which was then easily mechanizable. So yes, I think now it's okay to stop. That brings me to the end of the talk. And from a verifier or verification perspective, of course, the code is the beginning, but for the proof, for the verifier, the invariants and the abstraction functions are key. And the main invariants are good for intuition, like 3 times m is greater or equal n, but the formal proofs typically need much, much more. and they are often, unfortunately, unsuitable, or fortunately maybe for the audience, unsuitable for presentation in a course or even a book. So it was easy enough to put the single-ended cue, the normal cue, into the book, but I don't think I will put the double-ended one into the book because it's just, there's too much detail, and I don't think you could of course present some high-level view of it, but then the question is what is a high-level view doing in a book that's about mechanized proof? Shouldn't you also present more? I'm still torn there. What would be interesting to try other systems, for example, the Y3 system, whether it could automate more of the queue and especially the double-ended queue verification. I'm sure there is potential for automation, but yeah, once you've done it, you don't want to go back and automate. At least I don't feel so. And what I would be interested in is a verification of the lazy version that Xavier presented. Maybe he knows about. You referenced a paper, but I think that was about thunks. And yeah, so it was definitely the imperative and not the lazy version. Yeah, at the very.
No, the paper by Potienko.
Yes.
No, I think we have some laziness in there.
Ah, okay.
I think François is online, so maybe he will.
Okay, then he can comment on that. That would be nice. And I think that is really the end and my last slide, and I'm very happy to take questions.